Hey you guys, this is Mr. Millings, and in this video we are going to go through a few mixed gas law problems. So far this unit, in the gas law unit, we have been learning about several different gas laws. We've talked about Boyle's law, which states that the pressure and volume of a gas are inversely proportional. As one is increasing, the other is going to decrease. We've talked about Charles' law, which states that the volume and temperature of a gas are directly proportional. As one is increasing, the other will increase as well. We've talked about Avogadro's law, which states that the volume and number of moles of a gas are directly proportional. If the number of moles of gas is increasing, then the volume will also increase. They're directly proportional. We've talked about Gay-Lussac's law, which states that the pressure and temperature of a gas are also directly proportional. If the pressure of a gas is doubling, it's because the Kelvin temperature of that gas is doubling. And we also talked about the combined gas law, where we can essentially combine Boyle's law and Charles' law and Gay-Lussac's law into this formula that we see right here. P1V1 over T1 equals P2V2 over T2. And so what we're going to do in this video is we are going to use these 5 formulas here to solve 5 different example problems. And I'm going to show you how to apply one of these gas laws to a given word problem, how to figure out which gas law you are going to use to solve that particular problem. So let's jump right in with our very first example, and hopefully you catch on. In this very first example, it says that 5.00 moles of helium gas is added to a sample of gas that initially contained 1.75 moles of helium. If the final volume of the sample is 22,950 milliliters, then we need to determine the initial volume of gas in liters. So whenever we come across these word problems here, what I like to do is make sense of it. I like to go through these little word problems and label what's going on. If we take a look, this tells us that the sample of gas initially contained 1.75 moles. What does initially mean? That means originally, the very first, right? Starting out, that's what it contained. So if we take a look, 1.75 moles, we know that N is the variable that we're going to use for moles, and since it's telling us right here that initially contained this many moles, this is going to be our N1. And if we read this word problem, 5.0 moles of helium gas is added to this amount right here. So from that, we should be able to get N2. So we know that N1 is going to equal 1.75 moles. And if we're adding 5 moles to this right here, then N2 is going to equal 5.00 moles plus 1.75 moles. And N2 ultimately is going to equal 6.75 moles. Okay, so we know N1 and we know N2. Let's read the question further. It says if the final volume, so final volume will be V2, is 22,950 milliliters, then what we need to do is determine the initial volume. Remember, initial means first. So what we want to find here is V1. And last, if we take a look, we want to figure out the gas in liters, not milliliters like we see V2 is in. We want to figure this out in liters. Okay, so if we take a look at this problem right here, we have a bunch of variables, and if we take a look, we have a bunch of variables that have V's and N's, V's and N's. What formula is that going to be? Well, that's going to be Avogadro's law, right? Avogadro's law. And Avogadro's law states that V1 over N1 equals V2 over N2. And so all we now need to do is go ahead and manipulate these variables around and solve for V1. So how do I get V1 all by itself on one side of this equal sign? Well, I don't like fractions, just like you probably don't. And so what we can do is we can cross multiply. And if we cross multiply, we're going to end up with V1 times N2 equaling V2 times N1. And remember, we're trying to isolate V1. We're trying to get V1 all by itself on one side of the equal sign. So we need to divide both sides by N2. If we divide both sides by N2, N2 is going to cancel on the left-hand side. And the formula that we're going to use to solve this problem is V1 equaling V2 N1 all over N2. So there's a lot of setup just before we even begin to plug these numbers in. So now that we know our formula, what we can start to do is plug these numbers in. So V1, to get the initial volume, we're going to take V2, which is 22,950 milliliters. But if you take a look, we want our final answer in liters. So let's go ahead and convert this to liters. The way that we're going to convert this to liters is by sliding this decimal 3 times to the left, and we'll end up with 22.950 liters. So we have 22.950 liters times N1. If we take a look at this problem here, N1 is 1.75 moles. And we're going to end up dividing this by N2, which is 6.75 moles. So now what we can do is we can take our calculator out and plug these numbers in. We have 22.950 times 1.75 divided by 6.75, and we're going to end up with a final answer of 5.95. 5.95 what? Well, we take a look, moles on top and bottom are going to cancel, leaving us with liters. So it looks like our initial volume of this gas is going to end up being 5.95 liters. Let's take a look at another example. In this second example, it says a sample of argon gas is initially in a 7.57 liter container. The gas is then moved to a 1334 milliliter container at a temperature of 118 K. We need to determine the initial temperature of the gas in Celsius, right? In Celsius. So if we take a look at this problem, a sample of argon gas initially in a 7.57 liter container. Initially means first, and liters is volume. So here's our V1. The gas is then moved to a 1334 milliliter container. So the gas is moved, and so it looks like this here is going to be our V2. Milliliters is a measurement of volume, and this is our second volume of the gas if it's moved to a new container. And so the temperature of this gas in this new container is 118 K. And we need to determine the initial temperature. Initial means first. So what we need to figure out is the initial temperature of the gas, but we need to figure it out in Celsius. So if we take a look at our word problem here, we have a bunch of V's and T's, right? V's and T's. And so what formula uses V's and T's? Well, that's going to be Charles' law, right? If we remember from an earlier video, Charles' law states that the volume and temperature of a gas are directly proportional, right? And so we know that V1 over T1 is going to equal V2 over T2. And so if we take a look, we see here that V1 is going to be 7.57 liters. We can see that V2 is equal to 1334 milliliters. We can see that T1 is what we're trying to find in degrees Celsius, and T2, it tells us, is 118 Kelvin. Okay, so we have a couple issues before we can start plugging these numbers in. This is in milliliters and this is in liters. And so we need to make these units the same. And it doesn't matter if it's in milliliters or liters as long as they're the same. So I'm going to go ahead and convert the milliliters to liters. And the way that we do that is by simply moving this decimal to the left 3 times. We have 1.334 liters here. So now the two volume units are the same. And whenever we work with any gas law problem, whenever we're working with one of these formulas, we always need to make sure our temperature is in Kelvin, which it is. So let's go ahead and solve this little problem. It looks like we're trying to solve for T1 here. And so I hate fractions just like the rest of us. So what I'm going to do here is I'm going to cross multiply to get rid of the fractions, and I'll end up with V1 times T2 equaling V2 times T1. And now we're trying to figure out what T1 is. So we need to divide both sides by V2 here. And so take a look. T1 is going to equal V1 times T2 all over V2. And so what is V1 in this problem? It's 7.57 liters times T2, which is 118 K. And we're going to divide this by V2, which is 1.334 liters. And so we'll get our calculator out and we'll go ahead and put this in. 7.57 times 118 divided by 1.334. And we're going to end up with a final, or an answer of 669.6. 669.6 approximately. What unit is this? Well, it looks like we have Kelvin. But the question here is asking us for Celsius. So how do we go from Kelvin to degrees Celsius? Well, to go from Kelvin to degrees Celsius, we have to subtract 273 from our Kelvin temperature. And so what we'll do here is we'll take 669.6 minus 273, and we will end up with a final answer of 396.6 degrees Celsius. So this is going to be our initial temperature of this gas in degrees Celsius, 396.6 degrees Celsius. Okay, let's take a look at another problem. In this example right here, it says that a sample of neon gas initially has a pressure of 5.78 atmospheres and a temperature of negative 114 degrees Celsius. It is then cooled to a temperature of 283 K. We need to determine the final pressure of the gas. So let's take a look at what's happening here. It looks like we have a sample of neon gas that initially means first, has a pressure of 5.78. So this looks like this is going to be P1, 5.78 atmospheres. And while it's at this pressure, it's also going to be at this temperature. So this is going to be our T1. If we take a look, this gas is then cooled, so there's a change that's taking place, and that the new temperature now is going to be 283 K. So here is our T2, and we need to find our final pressure of the gas. So what are we trying to figure out? Final pressure, P2, is what we are asked to figure out. So now that we've kind of labeled everything, let's take a look at this word problem. You need to ask yourself, what formula do I know uses P's and T's? Well, that is going to be Gay-Lussac's law. Right? Gay-Lussac's law, which states that the pressure and temperature of a gas are directly proportional, or P1 over T1 equals P2 over T2. Now, before we start working with this formula, let's figure out what's happening. Let's figure out what P1 is. Let's figure out what T1 is. And let's figure out what T2 is before we plug them into the formula. So if we take a look, P1 is 5.78 atmospheres. P2 is what we're trying to figure out, so we can leave our final answer in atmospheres since the question doesn't tell us to put it in a specific unit. T1, if we take a look, T1 is negative 114 degrees Celsius. However, whenever we work with any of the gas laws, our temperature has to be in Kelvin. So how do we convert Celsius to Kelvin? How do we go from Celsius to Kelvin? We must add 273 to our degrees Celsius. So let's add 273 here, and we will end up with 159 degrees, 159 K. So there's our Kelvin temperature. And if we take a look, it looks like T2 is already in Kelvin, 283. So now that we have everything set up, let's go ahead and figure out what P2 is going to be. I don't like fractions just like the rest of us, so the way that we're going to get rid of these fractions is to cross multiply. And if we cross multiply, we're going to end up with P1 times T2 equaling P2 times T1, and in this problem we're asked to solve for P2, so we need to get rid of T1 from the right hand side here, and we'll divide both sides by T1. T1 is going to cancel, and so the formula that we're going to use to solve this problem is P2 equals P1 times T2 all over T1. And so what is P1 in this problem? It looks like it's 5.78 atmospheres. What is T2 in this problem? 283 K. And what is T1 going to be in this problem? 159 K. So let's get our calculator out. We have 5.78 times 283 divided by 159, and we're going to end up with 10.3 approximately. Kelvin is going to cancel, leaving us with the unit ATM, and 10.3 atmospheres should be our final pressure of this gas. Alright, so this is a Gay-Lussac's law problem. Let's take a look at another example. In this fourth example, it says a sample of neon gas has its initial volume and pressure of 3,729 milliliters and 616 millimeters of mercury, respectively. If the gas is moved to a new container with a volume of 5.99 liters, a pressure of 5.99 atmospheres, and a temperature of 365 K, what was the initial temperature of the gas in degrees Celsius? So there's a lot going on here, a lot that we have to decipher and figure out what's happening. So let's take a look. It tells us right off the bat that this gas has an initial volume. That means a first volume and first pressure of this right here and this right here. So milliliters is volume. So here's our V1, and millimeters of mercury is pressure. So here's our P1. The gas is then moved, so there's a change, right? There's a change in this gas. It's moved to a new container, and so the volume of this gas is going to become 5.99 liters. This is going to be your V2. A pressure of 5.99 atmospheres. This is going to be our P2, and a temperature of 365 K. This is going to be our T2. We need to figure out initial temperature. Initial means first. And last but not least, it's telling us that this temperature right here, needs to be in degrees Celsius. So there's a lot going on here, so let's jump right in and figure out what's happening. So if we take a look at this problem, we have a bunch of P's, we have a bunch of V's, and we have a bunch of T's. So what formula do we know uses P's, V's, and T's? Well, that is going to be the combined gas law. So it looks like this is going to be a combined gas law problem. And the combined gas law tells us that P1 times V1 over T1 equals P2 times V2 over T2. So let's set everything up over here. If we take a look, it looks like we know what P1 is. P1 is going to be 616 millimeters of mercury. It looks like we know what V1 is. It's 3,729 milliliters. T1 is what we're trying to figure out. We want to figure this out in degrees Celsius. Let's take a look at what P2 is. It tells us that P2 is 5.99 ATM. It tells us that V2 is going to equal 5.99 liters. And it tells us that T2 equals 365 K. And so there's a lot happening before we can even plug this stuff into the formula. If we take a look, our pressure units are different. This is millimeters of mercury, this is atmospheres. We need to make these both the same. And it doesn't matter if we use millimeters of mercury or atmospheres for the combined gas law problem. So let's go ahead and convert this. Let's convert the millimeters of mercury to atmospheres. So P1 is equal to 616 millimeters of mercury. We want to convert this to atmospheres. We know that 1 atmosphere is 760 millimeters of mercury from an earlier video. And so we'll put this in our calculator, and what we end up with is 0.8105. 0.8105 atmospheres. So there, now our pressure units are the same. We have atmospheres here and we have atmospheres here for P1. If we take a look, our volume units are different too. This is milliliters, this is liters. Which one do you want to use? It doesn't matter. We'll get the same answer either way. So let's go ahead and convert this to milliliters. We do that by sliding the decimal to the right 3 times or multiplying by 1,000, and we'll end up with 5,990 milliliters. So now we have milliliters here and milliliters here. And before we can even plug stuff into our formula, the temperature needs to be in Kelvin, which it is, but our final answer needs to be in degrees Celsius. So once we plug all this stuff into our formula, We'll just have to convert it to Celsius by subtracting 273. So let's get rid of these fractions here first and cross multiply. And if we cross multiply, what we will end up with is P1 V1 T2 equaling P2 V2 T1. And we're asked to figure out T1 here, so we're going to divide P2 and V2 to get rid of it from this side. And what we do to one side of the equal sign, we must do to the other. So this is going to cancel. And so now the formula that we're going to use to solve this problem is T1 equaling P1 V1 T2 all over P2 times V2. And so in this problem here, let's take a look. What is P1 going to equal? It looks like that's going to equal 0.8105 atmospheres times V1, if we take a look, 3,729 milliliters, times T2, if we take a look, 365 K, all divided by P2, which is 5.99 atmospheres, times V2, which is going to be 5,990 milliliters. Holy shnikes, a lot going on here. So let's go ahead and put this in our calculator. We'll take 0.8105 times 3,729 times 365, and we're going to divide this by, and we'll put everything in our calculator that's in the denominator in parentheses, 5.99 times 5,990. We'll close those parentheses. And then it looks like we're going to end up with a grand total of 30.7. 30.7 what? Well, let's take a look. Milliliters will cancel, ATM will cancel, and so it looks like Kelvin is left over. But our final answer needs to be in degrees Celsius. So how do we go from Kelvin to degrees Celsius? We subtract 273 from our Kelvin. So one final step here. We have to get our degrees Celsius, right? And so to get our degrees Celsius, we take our Kelvin temperature minus 273, and we should end up with negative 242 approximately. Alright, so that was a very long problem, but it looks like the initial temperature of this gas is going to be negative 242 degrees Celsius. Let's take a look at one final problem. In this final example, it says a 4.96 liter sample of helium gas is moved into another container with a volume of 1.25 liters. If the final pressure of the sample is 19.7 psi, then we need to determine the initial pressure of the sample in atmospheres. So if we take a look here, it looks like we have a sample of helium gas, and this is our V1. Tells us it's liters, so this is our starting volume of this gas. It's being moved to another container that has a different volume, so this here is going to be our V2. If we take a look, the final pressure of the sample is this right here. So this here is going to be our P2, our final pressure. It says to determine the initial pressure. So P1 is what we're trying to figure out in atmospheres. So if we take a look here, you got to ask yourself, what formula do I know uses P's and V's? Well, that's going to be a Boyle's law problem, right? Boyle's law is the relationship between the pressure and volume of a gas, provided that the temperature and number of moles of gas are being held constant. So we know Boyle's law is P1 V1 equals P2 V2. And before we start plugging numbers in, let's go ahead and figure this out here. Let's figure out what P2 is. Let's figure out what V1 is. Let's figure out what V2 is, right? So if we take a look here, V1 is going to equal 4.96 liters. V2 is going to equal 1.25 liters. This tells us that P1 is what we're trying to figure out, right? We're trying to figure out the initial pressure. So we want to figure this out, but it needs to be in atmospheres. And then it tells us that the final pressure is 19.7 psi. So if we need to figure out the final pressure in atmospheres, we should probably first just go ahead and convert this right here to atmospheres. So how do we convert PSI to atmospheres? We have 19.7 PSI. We know that 1 atmosphere from an earlier video on pressure unit conversion is 14.69 psi. So we'll put this in our calculator. We'll take 19.7 divided by 14.69, and we're going to end up with 1.34 approximately, 1.341 psi. So P2 is equal to 1.341 psi. So now, I'm sorry, this is atmospheres, I apologize. PSI is going to cancel, leaving us with atmospheres. Atmospheres, I apologize. So 1.341 atmospheres is our P2. So now the pressure units are the same, right? We have atmospheres here, and take a look. We have liters here and liters here. And so now what we're asked to figure out is what P1 is going to be. So how do we get P1 all by itself on one side of the equal sign? Well, we divide both sides by V1. V1 cancels here, and so the formula that we're going to use to solve this problem is P1 equaling P2 times V2 all over V1. What is P2 in this problem? P2 is going to be 1.341 atmospheres. What is V2 going to be? V2 is going to be 1.25 liters. What is V1 going to be? It's going to be 4.96 liters. And so when we put this in our calculator, 1.341 times 1.25 divided by 4.96, we end up with 0.338 approximately, 0.338. If we take a look, liters cancels with liters, leaving us with atmospheres. So that is going to be our initial pressure of this gas, okay? So if you like what you see, go ahead and click that little bomb in the bottom right hand corner, and that's going to subscribe you to my channel. And feel free to leave any comments or questions in the comment section down below. And I really hope you guys found this helpful.